Okay, and then you would find the sum of all the x and y components. So if I draw my coordinate system over here, I'll have 4 vectors on this. I'll have E1 in this direction, E3 in this direction, and then I'll have E2y here, and E2x here. Then I add up these vectors, saying E3 minus E2y is equal to the y component of my net vector, and then E1 plus E2x is the x component of my net vector. And so my final electric field vector will be Ex in the I direction plus Ey in the j direction. But then make sure you can find the magnitude and the direction. So the magnitude of that is going to be Ex squared plus Ey squared. And then the angle for this will be the inverse tan of Ey over Ex. All right. Yours isn't going to be this complicated. Yours will be quite a bit easier than this, but the basic idea will be the same. You won't have as many vectors to deal with. You only have maybe 2 vectors that you have to deal with, whereas here you have 4 vectors to deal with. So it'll be a simpler problem, but doing the same stuff. Make sure that you know your trig stuff, and make sure you know how to find the resultant, the magnitude and the direction of a vector. Can y'all do this? We've done it a bunch of times. I just want to make sure that you can do it before we move on, or before you move out. If I can move up and go to college. Good job. Okay? Is this okay? I can do this? It's question number 1. Is find the electric field at this particular point. Imagine you have a positive charge there. What is the force on that positive charge? That's the direction of your electric field. And then add up, do the vector addition. Okay? Cody? It's okay.
Yeah, I think so.
I know. The potential is a lot easier. So I'm going to erase all this. The potential. Actually, let me just show you the force first, because the force is similar. It's going to be 2 charges. I ask you what is the magnitude and direction of the force. Let's just say as these 2 charges, it's going to look a lot like this, okay? I ask you what is the direction of the force on, say, this charge. The direction of the force on this charge is in this direction, because this one's positive, this one's negative. So my force is in that direction. You need to know how to figure out this angle based on the sides of the triangle. And then you also need to know how to calculate the magnitude G, what is the charge? It's KQQ over R squared. These are all on your equation sheet, these equations, but make sure that you know them. Okay? This is a lot like the electric field, just dealing with vectors.
Yeah, on the same exam, number 20, do you mind looking over that?
Can I do potential first?
Oh, please.
Cody had asked for potential. Like I said, first problem, potential, electric field, and force, all in one problem. And it's worth like 20 points, so make sure you can do it. To find potential, say if I want to know the potential at point A, I do the sum of KQ over R. So that would look like this. It would be 9 times 10 to the 9th, that's K, times this charge, 9 times 10 to the minus 9, divided by R, that's this distance, which is 3 meters. Alright, this is positive, so I keep it positive. Plus, this charge, K times plus 50 nanocoulombs. Sorry, my pen's messing up. Divided by this distance, which is 5 meters. Notice it's not squared like it is for the electric field. Plus K for this charge is going to be minus 16 divided by this distance, which is 4. And then these are scalar quantities, so they just add up. Notice that there are lots of things that cancel out. These cancel. This cancels with that partially. So I get 27 plus 90 plus minus something. Make sure you get the negative. If you have a negative charge, it carries a negative potential. And when you add them up like scalars, you subtract it instead of adding it. Okay? There'll just be 2 charges, so it'll be a lot easier than this one. but it's similar to this one. If you can work through this field problem, you'll be good. And then there's a potential problem on exam 2.
That would have been a potential, which is just.
Right, this is the potential. Exam 2 has that potential one, but it looks a lot like this. Is that okay with this one, everybody? Problem number 1, 20 points. Okay, number 20, you're not going to do any derivations. And this is sort of a derivation. Okay, so as I told you, I think this was your only derivation on any of the exams, but you're not going to have any derivations. Anything else from this exam? Let's just sort of scroll through. Oh, good? Want to get the second exam now? All right. Okay, we have capacitor circuits, resistivity, Ohm's law, combination circuits. There are 4 possible circuits you could have, right? Or is it 3? Or as far as the basic circuits, you could have a capacitor circuit, combination capacitors like we had. Or you could have a combination resistor circuit, or you could have a multi-loop circuit. You'll have at least 2 of those. And they won't be quite as complicated as what we had on the exams, because we just don't have as much time for more problems. But they'll be similar, so if you can work through those, you'll be good to go. Let's see, you'll see multiple choice, it'll look similar to these. RC circuits, your home circuits, make sure you know those 3 basic things that operate the home. Multi-loop circuits, know how to write the equations. In fact, you will have a multi-loop circuit, so I think I told you that already. Oh, this is 102. I'm sorry, but all those things hold. Let's look at, here's your 202. Okay, this was also including our electric flux stuff and Gauss's law, capacitor circuits, potential. Any of these multiple choice stand out to you? No? All right, think about it. We'll go back and look at the free response. Finding the potential or the electric field due to a potential function. This is where you do your, your partial derivative. So something like this, I give you a similar problem. I change the function, maybe change the coordinates. Make sure you can do partial derivatives. Remember on this that our electric field, Ex, the x component of our electric field is just the negative of the partial of v with respect to x. The y component is the negative of the partial of v with respect to y. So for example here, it's going to be negative of 3y, and just negative of 3y. I just treat anything that's not here as a constant, just as a number. Oh, there is a derivation here, but you're not going to see any derivations. All right. Here's potential and potential energy. So we worked the potential problem already, but it could be something very similar to this. Remember, to find the potential energy of a configuration of charges, our potential energy is K, Q, Q over R for 2 sets of charges. And the way we did that is we found the potential energy for these 2 charges, letting that fill those places here and here. Then we found the potential energy for these 2 charges. And then we found the potential energy for these 2 charges. We have 3 possible configurations. Once you find those 3 potential energies, you add them up. Make sure you keep your signs. So if I have a negative and a positive, I have a negative potential energy. And then it adds up like scalars. Okay? Scalar quantity, potential energy. C? Mm-hmm. Does anybody know what the potential was right here? Does anybody have the solution to this? For part A? Okay, so for part A, you'd find that the potential at this point is 81 volts. The work required to place a 2 nanocoulomb charge there is equal to Q times delta V. This sort of comes from our basic definition of potential, Remember, potential is energy over charge, energy per unit charge. We can also think of it as work per charge. So then our work is Q times V. But here we're looking at a change in potential. So I'm taking something from way over here, where my potential is 0, to over here, where my potential is 81 volts. And so the work that's going to be required to do that is going to be equal to 2 nanocoulombs, or 2 times 10 to the minus 9 coulombs, times 81 volts. That 81 comes about, it's our V final minus V initial. Right, V final is when I get to this place, it's 81 volts. V initial is way over here at 0. And so my work is just 81 times what I found in part A. Or excuse me, 81 volts times my charge. Okay? That's the easiest way to approach that. Brett, did you ask that? Yeah, is that clear? All right, capacitor circuit. This one didn't work out evenly, but if you have a capacitor circuit, you'll either have a combination resistor or a combination capacitor circuit. They work out similarly. So I'll give you one, and I'll ask you what is the charge or what is the equivalent capacitance, and then what is the charge and voltage on any one of the capacitors. Or if it's a resistor circuit, I'll ask for the current and the potential on any one of the resistors. Okay, so you'll have a multi-loop circuit, and then you'll have one of these, either one of these or one with resistors. We've had both. It will work out evenly, so you should, if you're good with circuits, you'll just be able to look at it and say, oh, boom, 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 boom. Or if you have to go through it a little more slowly, that's okay too. It really helps me to draw the circuit as I move along.
Through just the basics.
Sure thing. Yeah. So with these, you just want to identify what's in parallel and series. So with this, you would look at this and say, this is a parallel branch, and this is a parallel branch. And then within them, they both have series branches here and here. You can tell that because you follow along, you come here, and you say, oh, I split up here. I go 3 ways. I go here, and I go here. So I could collapse all of this down to a single point, and I could draw it like this. That's C1, here's C2 and C3, and there's C4. And then I have, they all come together right here, and then they form another parallel branch. I have 2 capacitors up here, and then I have another one down here. So my circuit, the first step is just figuring out what it, sort of drawing it on this, in this way. I find it easier to see it like this. And then I can identify, I have a 3, and a 6, and a 6. And here I have a 4, and a 2. Then you start finding your equivalent capacitance. 4 and a 4 in series, what's that? It is 2. It'll help you to know your fractions. So if I have a 1 over 4 plus 1 over 4, that's equal to 2. 1 over 2 plus 1 over 2, that's equal to 1. 1 over a third plus a 6 plus a half, that's equal to 1. Were there others? Oh, 3 and a 6. 2 6 plus 1 6 is 3 6, so that's 2. It'll help you to know those. That way you're not fumbling with the fractions, because you'll see these, some of these on the test tomorrow. All right, so I have a 4 and a 4 is a 2. A 3 and a 6 is also 2. And then I add up the ones in parallel. 3, 2, and 6. See, when I gave you this, I just wasn't thinking. I was thinking resistors, and so I was thinking 3, 2, and 6. Oh, that adds up to 1, but it doesn't, right? It adds up to 11, and that's why I got funky. So then I have an 11 microfarad capacitor, and I have a 4 microfarad. All right. Then I would find my equivalent, 1 over 11 plus 1 over 4, the inverse of that. And then I would find the charge on each capacitor. So recognize that capacitors in series have the same charge. So whatever charge I have here is also equal to the charge that I have there. Okay. You want me to go through the rest of them? Okay, so if I have, let's see, I have 1 over 11 plus 1 over 4. Does anybody know what this is? You have it, Riley?
2.9.
Okay, so we'll 2.9 microfarads. That means, I'm just going to call this 3, okay? To make it a little easier. The numbers will be a little off, but that's okay. So I have 3 microfarads. That means that I can draw this as a circuit. 3 microfarads, 12 volts. That means I have 36 microcoulombs on that 3 microfarad capacitor. So I have 36 microcoulombs here and 36 microcoulombs here. 36 divided by 4 is 9, so I have 9 volts there. And then I have approximately 3 volts here. Again, I rounded off, so it's not exactly right. I have 9 and 3. I know this has to add up to equal 12. Okay, the numbers will be even on the test tomorrow, whether you have a resistance or capacitors, so they'll work out a lot more easily. So I have 9 and 3. If I have 9 and 3, that means that I have 9 volts on this branch, and I have 3 volts on this branch. If I have 3 volts there, I have 3 volts here, and 3 volts here. And then up here I have 2 volts and 1 volt. And here I have 9 volts. And then I have 4.5 volts and 4.5 volts. Describe what I did there. So I have 9 volts across this part and this part because I have 9 volts here. I only have 1 capacitor here, so I have 9 volts. Here I have 2 equal capacitors, so they split it evenly because they're in series, so I have 4.5, 4.5. Down here, I have 3 volts across this whole thing. So I have 3 volts across this one, because there's just 1 capacitor. 3 volts across this one, just 1 capacitor. And here I have 2 capacitors. They're going to split up that 3 volts. The small capacitor has a big voltage, so this was our 3 microfarad, so it has 2 volts. Our big capacitor has a small voltage. Because they're off by a factor of 2, their voltages are going to be off by a factor of 2. Okay? That was kind of fast, but if you're not getting this, you should really go back and look at some of the other old tests, or even this old test, and work through those capacitor circuits. Because you'll see either a capacitor or a resistor circuit, and they both work out similarly, but a little bit different. Okay? Is that okay? Good? It's okay if you don't have it, but make sure that you get it before the test tomorrow, because you'll see one of these circuits. It'll be a little simpler than this, not as many capacitors or resistors, so that's good. Can I clear this? All right. Electric field, electric flux, Gauss's law to find the charge. Electric flux, or flux in general, came up several times, so I would expect to see flux. In general, when you're finding flux, whether it's gravitational flux or electric flux, here it was electric flux, you're doing the field, the electric field, dotted with the area. And remember, our dot product says that if my area and my electric field are perpendicular, there's no flux. So in order for this to work, my flux, and my field, and my area have to be perpendicular to one another. So for example, if I take this side, and I want to know what is my flux, well, my electric field here is going to be 3 times x, or 3 times 5, just leave this function up here, in the I direction, minus 4 times j. So that is my electric field. And then my area vector, dA, is going to equal to the area of the space. This is 3 meters by 3 meters, so it's equal to 9 meters squared in the I direction. The area vector will always be perpendicular to the surface. So here it's in the positive I, here it's in the positive j. On this outside face, it's in the positive k direction. Over here in the negative I, the back face is negative k. Alright, the bottom face is minus J. So you have 6 spaces. Often some of the fluxes will go to 0 for various reasons. I'll show you why. So look, on this one it doesn't go to 0. My flux is E, 15I minus 4J, times, or dotted with, 9I. I've already done the integral here basically, because when I find the area, that's like doing the integral. When I'm adding up the area, the dA, the integral dA, so I'll just leave that off. Here when I do the dot product, I'm just doing 15 times 9, so that's 90 plus 54, 144 Newton meters squared per Coulomb. Okay, so that's the flux for the outer face, or this right face. Notice that if I, let's see, where does it go to 0? Front and back. All right, because in the front and in the back, they're in the area vectors in the k direction, and it's perpendicular, yeah. And my electric field is in the I and J. So for the front face and the back face, the dot product goes to 0. Also for the left face, it went to 0 too, right? Because x is equal to 0 for the left face, and so my I component of the electric field goes to 0. And it's only the I component that matters because the area vector is also in the I direction. Okay? Once you find the flux, the charge is easy. That's just from Gauss's law, the whole Q enclosed thing. Okay? No good on fluxes? We've done it several times, so I would expect to see it. Pretty sure it's going to be on the test. It is on the test. Okay? I'm going to take this away. It's problem number 15, exam 2. Okay. That's it. Anything else on this test? All right, let's look at exam 3. All right. Ohm's law, stuff like that. Basic resistor circuits. Right-hand rule. Multi-loop circuits. As I said, you will see a multi-loop circuit. Although you won't be doing the Gaussian elimination stuff. Just solving system of equations. RC circuits. You have a few right-hand rule problems. Not that many, but you have a few. Make sure you can do a multi-loop circuit. Y'all can do a multi-loop circuit? Do I need to do it? Okay, so you write 3 equations. You want to write the good 3 equations. So, for example, here, I want to always include the loop that doesn't have a resistor, because that makes solving the equation a lot easier. So, for example, here, I would do maybe the big loop. That would be 3 minus 2I1. I'm taking my current to be in this direction. Plus 6 equals 0. I could also do the bottom loop here. Let's take I2 in this direction. That would be, I'm going to go in this direction, so it would be 5 plus 6I2. See, there are 2 directions. I pick the direction for I2 and the direction that I travel through the circuit. So here, I chose I2 to be in this direction, but now I'm going through the circuit in this direction. So I have plus 5. Since I'm going against the current, it's plus 6I2, and then minus 6, because I'm going from high to low potential. Now we also have to get I3 in there, so we'll do the junction rule. Let's take I3 to be in this direction, and we would have incoming currents, which is all of them. So I have I1 plus I2 plus I3 equals to 0. All right? And then I solve this system of equations. But the way I've set it up, it's really easy to solve. Solve this one for I1, I solve this one for I2, and then I just plug those in here to solve for I3. If you set it up correctly, it will be very easy to solve, because I will give you one where there is no resistor in one of the branches. It makes it a lot easier to solve the algebra. It's much easier. If you were to choose, what would make it more difficult? Choose the top branch, the loop rule, and the bottom branch. It's a little bit more difficult. There's some more substitution that has to go in. Always try to include that loop without the resistor to make your algebra a lot easier. I need to solve this? Is that okay? Remember to
chose the current from 5 volts to go to the left instead of the right.
yeah, it doesn't matter, right? You choose it whatever direction you want. Let's run through this right quick because I want to point something out. So here I'll get I1 equals 9 divided by -9 divided by -2, so it's 4.5. I2 -1 divided by 6, and then I3 then will be what's 1/6? What's 1/6? I forget. 0.16. Yes. So this would be -4.66. Right. That's right. Yeah. So that means that I3, I chose to be in the wrong direction. So I chose it to be to the left, but I3 will actually be to the right. So it would be 4.7, 1/6, 4.5. I2, I chose correctly to the left. I1, I chose correctly to the left. So you choose the directions based on does it come out positive or negative when you do the algebra. Okay? Okay, can I move on? What do people in a math class call one another? Algebros. Alright, I'm gonna clear this. Is that what y'all call one another? Algebros. What's up, algebro? You've never done that? Oh, okay. You have to do this, know your house. If you don't have this, you'll have it in multiple choice. Just know your systems. Could see a cross product. It came up a couple times. You'll probably see a cross product with either, you will see a cross product with either a force on a free particle or like we had on exam 4 where you have a wire in space and a force on that. Alright? Again, you'll see either one of these or like with the capacitor. They work similarly. This one was set up a little more nicely. I have 6 ohms. These add up to give me 2 ohms. These two add up to give me 3 ohms. And so all this goes down to a 2 and a 2. 2 ohms. 2 ohms. My pen is messing up, sorry. 2 ohms. 2 ohms. 12 volts. Sorry guys, so this is 6 volts and 6 volts. And then you can carry that on back. Oh, I can work through this if you like, but it works out a lot like the capacitor. Do you like? Do you like me to? Okay. Let me try to neaten it up a little bit. Alright, so if I have 6 volts on this capacitor, that means I have 6 volts across here, and I have 6 volts across here, and I have 6 volts across here. So for R1, my voltage is 6 volts. Up here, when I have the 2 and the 4, I have my bigger voltage across my bigger resistor. So I have 4 volts and 4 volts here, and 2 volts here. If you're uncertain about how those voltages are distributed, I have an equivalent of 6 ohms here, which would give me 1 amp. So I have 1 amp of current going through each. V is equal to IR, so 1 times 2 is 2. 1 times 4 is 4. Alright? So that gives me 2 and 4 volts on R2 and R3. And then down on the bottom is a little trickier, although not really, because this is equal to 2 ohms. I have 6 volts across it, so I'm going to have 4 volts here and 2 volts here. For a similar reason that I had up top. I have the bigger voltage across the bigger resistor, the smaller voltage across the smaller resistor. 2 ohms is twice 1 ohm, so the voltage will be twice whatever this voltage is. So it has to be 4 and 2, because 4 and 2 have to add up equal to 6. Alright, I'm going to have 1 amp going through here, so I'll have 1 amp, or 2 amps rather. Is that right? I have 2 amps, I'm sorry, I have 2 amps going through here because I have a 2 and a 1, so it's 3 ohms. So I have 2 amps, 3 ohms and 6 volts, give me 2 amps. 2 amps and 1 ohm is 2 volts. 2 amps and 2 ohms is 1 volt. So I have 1 volt here, or excuse me, no, I'm sorry, 2 amps and 2 ohms is 4 volts. So I have 4 volts here and 4 volts down here at the bottom. So R4 and 5 are both 4 volts, and then R6 is 2 volts. These work out very similarly to the capacitor circuits, but they're a little bit different. So make sure you can do both, because you can see either one. Okay?
For the current, you just say I equals V over R.
Right. Once you know all the voltages, you just say V over R is your current. So I'd say 6 over 2, 2 over 2, 4 over 4 for each one. RC circuit, we had similar circuits for the, what was it, the RL circuits. So they work similarly. You have either an exponential growth or exponential decay. Make sure that you know how to use those. They're on the equation sheet, so if you know how to get your way around the equation sheet, then you'll be good. But you know, that equation sheet has 50,000 formulas on it. It's like 3 pages. Okay? But make sure that you know it. You'll get it tomorrow. But make sure that you know what's on it. Resistivity stuff here. I think that was it. Okay, exam 3 good, Joe? Exam 4, we just did. Good news with exam 4 is we didn't have a lot of that junk. I mean, we had some of it, but we didn't have all the different circuits. So if it wasn't on exam 4, it's not going to be on the final. So like, for example, we didn't have forced oscillators. Where we do the RLC forced oscillator circuits. We had phasers, but we didn't have forced oscillators, so you won't see that. All right, a little bit of right-hand rule stuff, phasers, Faraday's law and Lenz's law. You will have to use both of those. Like, for example, with number 5 to find the direction. Do y'all remember how to do this? It comes up a couple times. Let me just remind you. So here, I have an induced current in this loop. The induced current is because of Faraday's law, because I have this changing flux, and that's going to induce a current. In this case, my current is in this direction. So it's producing a magnetic field that is into the page over here and out of the page over here. Remember, right-hand rule. Thumb goes in the direction of the current, fingers into the page, fingers out of the page. So up here, I have a magnetic field that is out of the page. I have a magnetic field that is decreasing. Because the magnetic field is decreasing, the induced magnetic field, I'm sorry, the magnetic field is doing what? It's increasing. The reason it's increasing is because this bar is moving closer, and the magnetic field is stronger here than it is here. So as this wire moves closer, my magnetic field here increases. Because it's increasing, the induced magnetic field is going to be opposite the direction of the already existing magnetic field. So my induced magnetic field in this coil will look like this, and then I use my right-hand rule to find the direction of the current. Magnetic field is into the page, so my current is going to flow in a clockwise direction. This comes up in the free response problems too, so it's an important thing to know. We'll see that. Y'all good on Lenz's law? It's Lenz's law. Yeah. So here, you can first recognize that F1 and F3 are equal, because here the magnetic field is not changing at all, right? Because it's constant, it's not changing, and so the force is going to be the same. So F1 is equal to F3. So I can get rid of this one, and this one. So it's either B or D. And then I want to know what is happening to the force. So let's see, how does it work? I have an induced magnetic field in some of these. So here my magnetic field is increasing as I pull it in this direction. So the induced magnetic field is going to be in that direction. Y'all follow me? And so that means that my current is going to be clockwise, like that. And then the force is the force on this leading wire. And so that force, I have a current that's down. My magnetic field is out of the page, so my force is in this direction. So there's a force pulling back in this direction on that leading wire. Okay, now on this other one, I have a decreasing magnetic field, so my induced magnetic field will look like that. It's decreasing because I'm leaving this area, and the magnetic field inside this loop is decreasing, and so it induces a current that basically fills in the gaps for that, Lenz's law. So here, my magnetic field is out of the page. That's going to be a current that is counterclockwise. So I have a current that's in this direction, in this direction. This back wire is in the magnetic field, so it's going to feel a force. I is down, its force is in that direction. The force on that wire is in that direction. And then we recognize that both of these forces are in the same direction, so F2 and F4 are also going to be equal. So that'll give us P. That's a complicated problem. It had lots of stuff going on in it. But make sure that you can apply Lenz's law. That's really the important thing. But then we also have the right-hand rule for figuring out the force on a current carrying wire.
There was one like that that was about flux instead, though, right?
Right, yeah.
But the flux would have been bigger on the second one than on the last one.
Right, yeah, the flux. You'll see what he's saying. That the magnetic flux here would be bigger than the magnetic flux here. Because here we have magnetic fields that are out of the page and into the page, so they'll cancel out. Here, our magnetic field is all out of the page. That's what you're saying, right? Was there a question like that? I don't remember that.
I don't remember doing one like that in class or something.
Oh, okay. Yeah, maybe so. All right. Transformers. Another right-hand rule problem. Or not right-hand rule. Cross product. You'll probably see a cross product, either like this or the free particle. Mass spectrometer. Most of y'all did pretty well on this page, actually. Our transformer. Formula is on the page. Make sure you know how to apply it. Let's see. This was LC circuit. This is the one, if you remember, where the energy goes back and forth. It's not damped. It just goes back and forth. This was wait, no, I'm sorry. It is damped. It's not an LC circuit. It's an LR circuit. This is the one where the current either has exponential growth or the current has exponential decay. It's a lot like the RC circuits where we have the e to the minus t over tau, or the 1 minus e to the minus t over tau. It's a lot like the RC circuits. I don't remember, probably would have put this on, I don't remember if I did or not. Either this one or the RC circuits, just so you can see that exponential decay. Okay? I'll get into that in PPM too, look at it more. We can come back to this if you want. This was a LRC circuit. This is not a forced oscillator, so this is the one where the energy, the current just oscillates back and forth. Because remember we talked about how the energies. The energy looks like that. Come back to this. And then this is Faraday's law, where our induced flux, our induced EMF is equal to negative N dphi dt. You have to determine the flux, B dot dA, and figure out how much it's changing in order to find the induced EMF. You also, a lot of people miss this, or miss part of it anyway, because they didn't determine the direction of the EMF correctly. Similar to those problems we were doing before, and they either didn't add or didn't subtract it the way they were supposed to with this battery, because this battery is driving the current in this direction. So if your EMF is driving it in the opposite direction, then they have two competing EMFs. Is this the last one on that test? Yes. What on this test stands out to you? Faraday's law, the LRC circuit, LRC, or the LR circuit. Okay, with the LRC, again, with all these, you just want to be clear what's on your equation sheet. So our LRC circuit is right here. It's the damped circuit. I thought I turned this off. Okay, so I'm looking at these things. I want to know the charge or the current, I think, at a particular time. No, I'm just looking for the charge. So here, I want to know the charge at particular times. So I say Q is equal to Q naught times e to the minus t over RT over 2L times our cosine function of omega prime t. You had to find omega, and then you had to find omega prime, though we saw that omega is actually equal to omega prime. That omega prime has this extra term in it that basically goes to 0 right here, this r squared over 2L. So our omega is just root of 1 over LC. And then you solve for whatever omega is. I forget in this one what it was. Do you know, Kylie?
Omega prime is
258. But omega was 258 as well. Right, they were both equal. And then you're just plugging in. You put in your omega here, 258. You put in your t as 0.1, your resistance, your time, and your inductance for L, and determine what is the charge. So it's not that hard. You have the equation, but I say it's not that hard. A number of you didn't get it completely right, but it's just being able to keep all the numbers straight. Okay. Let's see. When is the first time the charge on the capacitor is 0? Well, the charge on the capacitor goes to 0 when this term goes to see, cosine is 0 when it's equal to what? Pi over 2, yeah, 0 is equal to 1. So when that term is equal to pi over 2, omega t is equal, or t is equal, or excuse me, charge is equal to 0. when omega t is equal to pi over 2. And then you solve for t. So it's pi over 2 omega. And then the sketch of the current versus time, well, it starts at 1, so it looks like this. Because it's a cosine function. You just draw a cosine function. Okay? You see something like this, it'll be a lot like this. It'll have slightly different numbers, but it'll be a lot like this. Good to go on that? Yep. What else on this test? 16, 14, what's 16? Yeah, a number of you didn't get it quite right. I think maybe my sleeve. I'm gonna roll up my sleeve. Is that okay? Does it seem more casual now? Are you gonna break out a beer or whatever? Okay. So here I want to know the magnetic flux at 2 seconds. The magnetic flux is B dot dA. So B is at 2 seconds is just this function at 2 seconds. 6 times 2 plus 5 times 2 squared. A number of you found the actual derivative, which is not the magnetic flux. That's finding the actual induced EMF. So that's 12 plus 20, 32. So this is equal to 32 times the area. The area of this loop was given as 0.01. So that's 0.32. That's the first answer, just the magnetic flux at t equal 2 seconds. Just evaluate the function and then multiply that times the area. And then the magnitude of the EMF, B, is the induced EMF is d phi dt. It's actually the negative of that, but the negative just has to do with the direction, so I'll just leave the negative off. And there's an n here, but there's only one term. D phi then is going to be A times dB dt, because the area is constant. 0.01 times dB dt, which is going to be 6 plus 10t. That's the derivative of this function. The derivative of 6t is 6. The derivative of 5t squared is 10t. And then you plug in t equal 2 seconds. 6 plus 20 is 26. So it's 0.26 volts. That's my induced EMF. And now for part 3, we need to know the magnitude and direction of the current in the loop. There are a couple things you have to do here. You first have to figure out the direction of this induced EMF. Well, I know my magnetic flux is increasing. As time goes along, this function increases. All right? So my magnetic flux is increasing. If it was negative, it would decrease, but it's increasing here. If it's increasing, that means my induced EMF, my induced magnetic field is going to be opposite, like that. That's my induced magnetic field. So my current then, to give me that induced magnetic field, is going to be counterclockwise by my right-hand rule. So my current is in this direction, but notice that this battery is pushing a current in that direction, in the opposite direction. So I have two currents sort of meeting one another. So my total EMF is going to be 2 minus 0.26, which is 1.74 volts. This one is 0.26 volts. This one's 2 volts. So the net current will go in this direction. So because the 2 volts is bigger, it wins, basically. My current then is going to be 1.74 over the resistance, which was 3 ohms. It's approximately, what is that value? It's 0.58 amps. And it's going to be clockwise. So that's the answer. There were several things that went into that, with the Lenz's law and figuring out what is the direction of the induced EMF. And then don't forget about your battery that's already there. You can figure out how do those two add up. Do they either subtract or they add? It's a good problem. Okay. I clear this? Okay, that's okay. Everybody? All right. Anything else here? Again, if it's not on this test, it's not on the final. So those other circuits that we did, you're not going to see. Sure. All right, so this is exponential growth or decay. So if I want to look at the current versus time, remember as time goes along, as I put a current through this inductor will inhibit the current as it travels through. It's going to have an induced EMF that's opposite the EMF of the battery. And so if I just do part E first, my current then versus time grows like this. And it grows up to an equilibrium current when basically this just goes away. It just becomes a wire. And that's all it is. It's just a wire in a coil. So the equilibrium current then, A, is just V equals IR. So I is V over R, which is 12 over 3, which is 4 amps. So I'm going up to a maximum of 4 amps. How long does it take to reach that? Well, my current is given by this. My I naught times 1 minus e to the minus t over tau. That's on your equation sheet. Where is it? It's right here. So our tau is L over R. For an LR circuit, that's 8 over 3. So if I want to know the current, or how long does it take to reach that for B, for it to reach the equilibrium current, this is a lot like the RC circuits. Anytime I have an exponential growth, it's just 10 times the time constant. So the time is 10 times tau, or 10 times L over R, which is 80 over 3. And then C asks how long to reach 1/2 of that equilibrium current. So here I'm doing this. I say 2 amps, because that's half of 4 amps, is equal to 4 times 1 minus e to the minus t over 8/3. Solve that for t. Make sure you can solve that exponential for t. I don't know what t was. You know, kind of 1.9 seconds. All right, and then for part B, what is the energy stored? U is just 1/2 Li squared. By the inductor, this is on your equation sheet. You got 1/2 Li squared is going to be 1/2 of this times your current 2 amps. Two amps squared. 4 times 16. Or, excuse me, 4 times 4 is 16. And that's it. Is that good? It's a long test. Like, that's the hard part about it. There's a lot on it. And that's all of it together. I think y'all can do any one of these. Sort of just come to a shorter test. Any other questions? I appreciate you told me really well. It makes it a lot easier. It's really hard to grade, but it's a lot easier if you do it really well. Or maybe like you're not certain, just write it down. That's easy. Okay. Remember, I do give a lot of partial credit, so if you're not certain, write as much. Any questions? Okay, listen. I'll give you really 2.5 hours, but if you can't do that assessment, you can come back later in the day. I think that you'll be able to finish another 2 hours, both things, but if you have a test, whatever, 10:30 or 11, whenever they start, then we'll figure it out. Okay? See you in the morning.